Schrödinger developed an equation that could be solved to give wave functions and the energy levels for the electrons trapped inside atoms. These three-dimensional electron waves can be characterized by a set of three integer quantum numbers. And we're going to go over and look at we're going to look at the total of the four quantum numbers. We'll talk about the fourth one. And then we'll take a look at some different problems that can help us put them together and discover a little bit more how we relate each quantum number to the other. So the four quantum numbers are, first is the principal quantum number, which is given the letter N. And N can start anywhere from 1 to infinity. Now, N designates the shell. You can think of it as the energy level. And so when we're talking about N, if N equals 1, that would be the first shell. If N equals 2, that would be the second shell, and so on. This principal quantum number relates to the size of the electron wave. So the larger the number, the farther away the electron wave would be from the nucleus. The secondary quantum number, L, can have a value from L equals 0 all the way to L equals n-1. The secondary quantum number divides the shells into groups of orbitals that we call subshells. The subshells determine the shape. Now, the L quantum number, while it is an integer, was given a designation of a letter. So if L equals 0, we call that S. If L equals 1, it stands for P. L equals 2 is D. L equals 3 is F. And then so on it goes then like the alphabet G, H. You've probably only really dealt with S, P, D, and F because those are the only subshells we need to describe the electrons of the atoms in the periodic table. The third quantum number is the magnetic quantum number. It is given a symbol of M sub L, which we just say M sub L, and the sub means the L is a subscript. Now, M sub L can have a value from negative L, which remember L is the secondary quantum number, and integer numbers, whole numbers, through 0 to a positive L. The magnetic quantum number divides the subshells into orbitals. The final quantum number, which distinguishes the two electrons that are in an orbital, is the spin quantum number. That's called M sub S. There are only two values for M sub S, a plus 1/2 or a minus 1/2. We need the M sub S term, it's called the Pauli exclusion principle, because two electrons can never have the same quantum numbers. So we need to have these four quantum numbers to distinguish the two electrons in an orbital. Let's take a look at some problems and see how we can try to put these quantum numbers and their relationships together. So for example, if you have the textbook, I am looking at problem 7.93 in the review questions. And it says, what is the value for L? What is the letter code for a subshell with, and it tells me, L equals 1. So we know if L equals 1, the letter code for L equals 1 is a P. Remember, L equals 0 is an S, L equals 1 is a P, L equals 2 is a D, L equals 3 is an F. Letter B asks, what is L equals 3, the letter code? And so L equals 3 designates an F. Remember, L is the secondary quantum number and represents the subshell. Now let's take a look at 7.97. In 7.97, it asks what are the values for N and for L. And the first one it gives us is 3s. N is designated by the number that's in front of the sublevel. So N would equal 3. So a 3s means you're in the principal energy level or the principal shell of N equals 3. S is the sublevel, and this represents our L, and anything with an S has an L equal to 0. We can also have, the second one is 5d. So this number here is the value for N, and N equals 5 would be farther away from the nucleus than an N equals 3. The letter D represents the value for L, and L equals 2 when you have the letter D. So I want to look at 7.98. And in 7.98, it says, actually I don't want to look at 7.98. I'm sorry, I want to look at 7.99. And 7.99 says it gives us N equals 6. Says you have a shell of N equals 6. It wants to know what values can you have of L. Well, let's look back. If you looked back to the first page, we see that L right here can have a value from 0 all the way to L equals N minus 1. So L, whoops, I didn't change the, L will equal 0, 1, 2, 3, 4. Now N minus 1 for this case would equal 6 because N equals 6 minus 1, so that would be 5. So it could only go up to 5. And so for N equals 6, L could have the values of 1, 2, 3, 4, and 5. Now notice if you count it up, there are 1, 2, 3, 4, 5, 6 values for L. And that is actually something that is a generalization you can make. Whatever level you're in, that is the number of L values that are possible. So in this example, N equals 6, and there are 6 different L values. If N equaled 4, there would be 4 possible L values. If N equaled 2, there would be 2 possible L values. Remember, L is telling us the sublevel, whether it's an S, P, D, or F. Okay, so let's look at another example, and I'm just looking at 7.105. And 7.105 says, if M sub L equals a negative 4, what is the smallest value of L? That's what they ask us. It says if M sub L equals a negative 4, what is the smallest value of L? Okay, to figure out what the smallest value of L is, let's think of what the numbers M sub L can be. Remember, M sub L can be from a negative value of L all the way to a positive value of L. So if we have an L value of -4, that must, an M sub L value of -4, that would mean that L equals 4 must be the smallest, because that at L equals 4 would be the first time we would get M sub L equals to 4. So that would be the smallest L. The next part of this question wants us to know what would be the smallest value of N. Okay, so let's think about how N is related to M sub L and to L. So N can equal, starting at 1, all the way through to, L, didn't mean to put N, I meant to put L, starts at 0, I'm confusing my N's and L's, sorry, L starts at 0, and it goes all the way to N minus 1. Okay, so if we want the smallest N would stop at N minus 1. So if N minus 1 is 4, because my L is 4, then the smallest value of N would be a 5. Okay, let's look at another one. Let's look at 7107. It says, give the complete set of quantum numbers, and I actually want to turn this page because I think we'll want to do 7107. It says, give a complete set of quantum numbers for electrons that could populate 2p. So for a complete set of quantum numbers, we would need, there's 4. There's N, there's L, there's M sub L, and there's M sub S. So if we had a 2p, N would be 2. Now let's remember L can have a value starting at 0 and going all the way up to N minus 1. So if N is 2, that is 2 minus 1, so that would be 1. So for N equals 2, L could equal 0 or 1. So if L equals 0, okay, then I know M sub L equals negative L to positive L. And so if L is 0, then you can only have one number. That would be 0. And then M sub S could be plus a half. Or I could have 2, 0, 0, minus 1/2. The other one I could have a 2. And remember up here I said that L could equal a 0 or a 1. So then I would have 2, 1. Okay, if L equals 1, then M sub L could equal negative 1, 0, and 1. Okay, so M sub L could equal a negative 1 plus 1/2, or it could have the same 3 and then minus 1/2. Then we could have 2, and then that takes care of this one here. We could have L equals 0. And then L equals 1. And then M sub L equals 0 plus 1/2, or 2, 1, 0, minus 1/2. Because remember, for L equals 1, we would have 3 sublevels. Then we could have 2, let's see, 1 for m equals L, positive 1. And that could be plus 1/2 or 2, 1, 1 minus 1/2. So the first two sets, this is all for L equals 0, because if you look up here, L can equal 0 or 1. All of these, the 6 here, are for when L equals 1, because when L equals 1, we can have 3 different M sub L's. See, here's 1, 2, 3 M sub L's. And for each set, we can have a plus 1/2 or a minus 1/2. Now, one more example to take a look at, and this one is a challenging one. And I think it helps. It's 7.109. And I think it helps on this one to have an electron configuration in mind. So this 7109 says, okay, it gives you an antimony atom. So we have antimony, which is Sb. And it wants to know how many electrons have L equals 1. And then it also wants to know how many electrons have M sub L equals 2. So, okay, to do antimony, I'm going to go ahead to answer these questions. For me, it's helpful to see the electron configuration. There are simpler ways that or quicker ways you could do it, but let's just take a look at the electron configuration. So it's very long, and I actually don't want to write the condensed one. I'm just going to write it out because I think it will help you visualize what we have to do. I'm going to have to go down on the second line because antimony is way down in the 5th period. So 4s2, so I have to keep going down. 3d10, 4p6, 5s2, 4d10, 5p, 1, 2, 3. Okay. So it asks for L equals 1. How many electrons? Okay, so we know that each orbital has 2 electrons. For L equals 1, okay, so remember L equals 0 is S. L equals 1 is P. So anything that is in, any electrons in a P orbital would have L equals 1. So if I'm looking at that, okay, so I have 6 here, 6 more here, 6 more here, and 3 electrons here. Because anywhere there's a p sublevel, you have L equals 1. So 6 plus 6 plus 6, that's 18, plus 3, so you would have 21 electrons that have L equals 1. Now M sub L equals 2. Remember, to get an M sub L equals 2, let's think about it. Okay, when L equals 0, which is an S, right? M sub L can only equal 0. When L equals 1, which is a P, M sub L could equal -1, 0, or +1. So far we don't have anything. When L equals 2, which is a D, M sub L could equal -2, -1, 0, 1, and 2. Okay, right there I have a 2. Now if we kept going if L equaled 3, which is an F, M sub L could equal a -3, a -2, a -1, a 0, 1, a 2, and a 3. And so I would have a 2 here as well. But looking at antimony, I don't have any F's, so I won't have to look at that. So what I want to look at, if you see here, there's a 2 in my D's. So I'm going to go and look at my d orbitals. So I have d orbitals right here and d orbitals right here. Now I have 1, 2, 3, 4, 5 d orbitals total, but only one of those orbitals have m sub L equals 2. So that means there's only 2 electrons in each full d subshell that has m sub L equals 2. So I would have 2 electrons out of the 10 here that has m sub L2 and 2 total here. So a total on letter B of m sub L equals 2, I would have a total of 4 electrons.